equipotential surface, because it always starts to move in the direction of a field line. A plus charge in the direction of the field line, minus charge in the opposite direction. So if you're in space and you release a charge at 0 speed, it always takes off perpendicular to equipotentials. You have something similar with gravity. If you look at maps of mountaineers, contours of equal altitude, equal height, if you started skiing and you started at that point and you started with 0 speed, you would always take off perpendicular to the equipotentials. So this is the direction in which you start to move if you start off with 0 speed. I now want to give you some deeper feeling of the connection between potential and electric fields. And I want you to follow me very closely. Each step that I make, I want you to follow me. So imagine that I am somewhere in space at position P. At that position P, there is a potential, one unique potential, V of P. That's a given. And there is an electric field at that location where I am. And now what I'm going to do, I'm going to make an extremely small step only in the x direction. Not in the y, not in z, only in the x direction. If I measure no change in the potential over that little step, it means that the component of the electric field in the direction x is 0. If I do measure a difference in potential, then the component, the x component of the electric field, the magnitude of that, would be that little side step that I have made, delta x. It would be the potential difference that I measure divided by that little side step. And I keep y and z constant. And these are magnitudes. So that's why I put these vertical bars here. Equally, if I made a small side step in the y direction, and I measured a potential difference delta v, keeping x and z constant, that would then be the component of the electric field in the y direction. Earlier, we wrote down for E as a unit newtons per coulomb. From now on, we almost always will write down for the unit of electric field volts per meter. It is exactly the same thing as newtons of coulomb. There is no difference. But this gives you a little bit more insight. You make a little side step in meters, and you measure how much the potential changes. It's volts per meters. It is a potential change over a distance. So now I can write down the connection between electric field and potential in Cartesian coordinates. It looks much more scary than the nice way that I could write it down up there when I had only a function of distance r. And so in Cartesian coordinates, we now get E equals minus, that minus sign we discussed at length, and now we get dv dx times x roof plus dv dy times y roof plus dv dz times z roof. And what you see here, this first term here, including, of course, the minus sign, that is E of x. And this term, including the minus sign, that is E of y, and so on. And the fact that you see these curled d's, it means partial derivatives. That means when you do this derivative, you keep z and y constant. When you do this derivative, you do x and z constant, and so on. And so this is the Cartesian notation for which in 1802 you will learn, or maybe you already have learned, we would write this E equals minus the gradient of V. This is a vector function This is a scalar function, and this is just a different notation, just a matter of words, for this mathematical recipe. And you'll get that in 1802 if you haven't seen that yet. So I now want a straightforward example whereby we assume a certain dependence on x, and I give you, it's a given, that V, the potential, is 10 to the 5th times x. So that is a given. And this holds between x equals 0 and, say, 10 to the minus 2 meters. So it holds over a space of 1 centimeter. So the potential changes linearly with distance. What now is the electric field in that space? Well, the electric field, I go back to my description there, there's only a component in the x direction, so the first derivative becomes minus 10 to the 5th times x roof, and the others are 0. So EY is 0, and EZ is 0. So you may say, well, yeah, well, nice mathematics, but we don't see any physics. This is more physical than you think. Imagine that I have here a plate which is charged, it's positive charge. And the plate is at location X, and I have another plate here, say at location 0. I call this plate A, and I call this plate B, and this plate is charged negatively. So X goes into this direction. So I can put the electric field inside here, according to the recipe, minus 10 to the 5th, and it is in the direction of minus x roof. So x roof is in this direction. The electric field is in the opposite direction. And it's the same everywhere. And that is very physical. We discussed that when we discussed the electric field near very large planes, that the electric field inside was a constant, remember? And the electric field inside was sigma divided by epsilon 0, if sigma is the surface charge density on each of these plates. And we argued that the electric field outside was about 0, and that the electric field outside here was about 0. So it's extremely physical. This is exactly what you see here.